Okay. Uh, let, okay, let me share my screen.
Yep,
Okay.
everything's visible.
Hopefully this works, and hopefully my pen
Beautifully.
works. Uh, okay. Okay. All right. So, hi guys. Today I'm gonna talk a bit about waves and oscillation. Uh, this is the official title of the lecture that Zizan asked me to talk about. Uh, the informal title is basically just analysis of dynamical system. I'm not gonna write that down. Anyway, so basically we'll build on what Zizan taught you guys in a few lectures previously, and then we'll talk about, just perturbing the system a little bit and see what happens. Okay, so. Uh, I like to start with examples. So let's work through one example from head to toe, and then uh we'll see what we get out of it, okay? And how can it be more generalized? So this is the problem that you may have seen in other places. It's called the beat on rotating loop. So basically, the premise is very simple. So there's a loop, and then this loop is rotating at some angular velocity omega. All right, and then on this loop, there is a beat, okay, of mass m, and then like the beat is confined to only to be on this loop, and then it moves around and maybe it will have an equilibrium position. We don't know yet, but let's analyze the system and see what we get. Okay, so the first thing you ever do when you encounter a physical system, some mechanical system or physical system, you want to try to write down the equation of motion that you want to analyze. Okay, so in this case, we want to understand what are the dynamics of this bead over here. All right, so let's write down. Um, I'm gonna write it down in uh using the what we call using talks. So just to remind you about your lessons in previously. So let's analyze the talks. So basically, first of all, the bead has a weight mg, all right, and then this loop has a radius r. Okay, so if it's at some angle theta over here, then this guy is rotating around this small circle over here at the bottom. So trying to understand, how does this bead move along the loop at different datas, okay? So at this data, it also have a normal force, a normal reaction force, and then that's about it. That's all the forces that are acting on the bead. But because this is going into a circle, because the loop is rotating, so you also want at the end, so you're gonna have a net force that's basically a centripetal force, okay? So basically, these are the things you want to have. You have the normal force and your weight, and then it contributes to a centripetal force, giving this B to move around. Okay. So in your free time, you can write down the equation of motion for this in terms of the forces. I'm gonna write it down in terms of the torque. So what are the torques that are given by the normal force and the weight that allows this B to move around, the loop. Okay, so move along this direction. All right. So we know that the normal force is always tangential to this, so there's no torque by the normal force. Um, so basically, what you have is basically a torque from the weight. So the torque from the weight is basically mg. Okay, that's the force, and the uh, distance from the center to the beat is r. Okay, and then because uh there's a mismatch of an angle theta, so the torque is basically mg sine theta. All right. And you so okay, and this thing allows this weight basically if you let it go, the bead will move down the hoop. So what will happen is that this is a torque that moves it to negative thetas, so we have a minus sign in front. Okay. Um, at equilibrium, what happens is that this must supply the centripetal force. Okay. Um, So basically the centripetal force yeah. The centripetal force is also needed to be taken into account. So the centripetal force, okay, the better way of saying that is that this must be equal to the torque given by the centripetal force. I'm going to move it to the other side. So so the centripetal force gives you a torque, which is this is Fc. The centripetal force is m omega squared r, and r is the radius of the circle that is going around. So basically, in this case, the circle, okay, if you do some geometry, so this is the triangle, and then you have a radius r of the loop, and this is the small r that you want to have, and this is the angle theta. So you have r equals to r sine theta. Okay. Uh, so you have m omega square r sine theta for the centripetal force. And then this is again at a radius r. And the two guys are separated by the angle. The centripetal force and the is separated by this angle, which is 90 degrees minus theta. Okay, this is 90 degrees minus theta. So it's cosine of theta. And this entire thing must be equal to. So again, let me stress that at equilibrium, uh, these two must balance out. So this is equals to negative of this at equilibrium. But if it's not but otherwise the equation of motion, you need to account for that it's not in equilibrium. So you have equals to I omega, or the second derivative of theta. So I don't know if Zizan has used this notation before, but this is basically d over dt. All right. And basically I is basically for the bead is just trying to move around this hoop. So it's just mr squared. All right. And then for uh uh yeah, and then basically it's mr squared theta double dot. All right. So basically let's just write this here like this, and let's just write mr squared theta double dot, where I have d over dt is equals to this dot over here. All right. So this is the equation of motion, okay? This is what you have learned in the past two sessions. And first of all, let's try to find the equilibrium point, all right? So we can do some simplifications. We can cancel some factors of m and some factors of r, okay? And then what you get is that theta double dot is equals to, let's divide by another r. So we have omega squared sine theta cosine theta minus g over r of sine theta. All right. And at equilibrium, okay, theta double dot is equal to 0. There's no acceleration at equilibrium. So what you get is a few solutions. One of them is sine theta equals to 0, which means that the bead is either exactly at 0 degrees, so it is at the bottom of the loop, or it is at equals to, or theta equals to 90 degrees. All right. Oh, sorry, 180 degrees, and is at the top of the loop. All right. Or that if you cancel out sine theta over here, what you get is that cosine theta is equals to uh g over r divided by omega squared. Okay. Or there's an equilibrium point. Let's call it theta equilibrium is equals to some the arc cosine of g over r. Let's call this omega c divided by omega uh squared. Okay, let's just Okay. There's some interesting things over here. So first of all, first of all, that this equilibrium means that the beat is over here, some cosine. But this is only possible if this is only possible if omega c is smaller than omega. All right. So there's a critical value of the angular velocity of the loop of how fast this loop is rotating, such that this beat can actually uh have enough power to just stay at some non-zero angle, some non-trivial angle here, right? Um, because cost can only be between 1 and -1, and because this is surely positive, it can only be between 0 and 1. So this only works if omega is large enough. All right. So these are the equilibrium things that you try to understand when you uh, look at a system. But there's now a very interesting question. So, for example, what happens if we perturb the system a little bit? So, what I mean by perturb is that, initially, for example, that the beat, this is uh, this this loop is rotating at some omega, which is larger than uh, is rotating at some omega 0, larger than omega c. Okay, so the beat is already at equilibrium at some point. Okay, at some theta. All right, and at some theta. All right, and at some time, as it passed by, I turn down omega 0. I turn up omega 0. Sorry, I turn up omega 0 to some other omega. Right. So what happens is that, when I increase this omega, the equilibrium angle changes. So now this beat is not in equilibrium anymore, and then it will, then the beat will start to move because it is not in equilibrium anymore. So the new equilibrium, the new equilibrium is not the same from the previous part. So now we will need to analyze the full equation of motion. So uh let's remember that the equation of motion is this. So this is the full equation of motion. Now that it is not from equilibrium, we don't know. Uh so the new equilibrium is theta EQ, and now this was initially at some theta 0. All right. Now at some new equilibrium, now the equilibrium point is not where the beat is, it will start to move, okay? But let's say that this omega is not that much different from omega 0, such that, it is not displaced so much from the new equilibrium. So how do we newly, how to analyze the new system, okay? So basically, uh, the beat is now, okay, it was initially at some theta naught, but there is an equilibrium point here. Uh, Let me see if I'm right. If I increase omega, if I increase omega, cosine theta becomes smaller. So when cosine theta becomes smaller, it goes to higher places. Yes, so this is correct. So this is the new, theta equilibrium. So what happens to to the beat? Okay, does it drop down or does it go up and then settle at theta equilibrium, or what happens? Okay, that's the thing that we're trying to find out. What happens? The question is what happens to the beat when the system gains a new equilibrium point. Or in this case, what happens to the beat when it's displaced? It is displaced by some amount away from the equilibrium point. All right. So when we look at this equation of motion, this is an equation of motion in theta. So basically, it's saying that, okay, how does this beat change in the angle theta measured from the bottom of the hoop. Okay, it's measured from the bottom of the hoop. We want to know like how does this the equation motion basically tells us, how does the bead move uh in terms of the angle. All right. But because we're looking at some place that's away from an equilibrium point, one thing that we can do right now is, just to set a new. So here's what we're gonna do. Here's our strategy. We're gonna set a new dynamical variable. Uh, Another way to put it is a new coordinate system, which is more helpful. So instead of using theta, which is measured from the bottom of the hoop, what we want is to define some angle. We know that uh, we can say that we can define that theta of the bead is basically the equilibrium angle, theta equilibrium, the new equilibrium point, plus some deviation from it, okay? So basically, we're saying that there's this new equilibrium point. There's this new equilibrium point, and the bead is displaced, all right, by some angle delta, you know. So in this case, delta is positive, and if it's a little bit below it, so delta is negative. So delta is negative. Okay. So instead of looking at the equation motion of theta, let's try to analyze, the motion of the bead um, when in this new variable delta. Okay. All right. So this is what we're trying to do. So if we recall our equation of motion, we can rewrite everything in terms of delta. Rewrite theta in terms of theta EQ and delta. All right. So first of all, theta equilibrium is a constant at this point. It's completely determined by, the new angular velocity, and G and R. So this is a constant. So basically, the only time, uh, the only thing that's changed with respect to time is the displacement of the beat with respect to the new equilibrium angle. So, is delta. And we can write everything as previously, okay? So you have sine delta theta equilibrium plus delta, cosine theta equilibrium plus delta. Minus G over R is omega C squared, as we defined before. And we have sine theta equilibrium plus delta. All right. Okay. Uh, so we can, we know how to expand sines and cosine. So sine x plus y is equals to sine x cos y plus cos x sine y. And then cosine of x plus y is equals to cos x cos y minus sine x of sine y. So what you can do is you can try to so let's yeah so before we do this, maybe we can rewrite this equation of motion a little bit tidily. So we can factor out sine EQ plus delta, and that's omega squared cosine theta EQ plus delta minus omega C squared. Okay. All right. Up until here, is there any questions? So if you have any questions, just feel free to unmute and ask or type in chat. Uh, is there any questions up to now? If not, I'll continue. All right. So basically, let's remind ourselves we have rewritten everything in terms of theta and delta. Now I just want to, make this a little bit more clear. So let's just use the sign addition formulae to rewrite everything. So basically, the first thing is sine theta EQ cos delta, all right, plus cosine theta EQ sine delta. And then there's going to be omega squared, cosine theta EQ, cosine delta, minus sine of theta EQ uh, sine delta, and then minus omega c squared. Okay. Now, from Zizhen's first lecture, you know that. So, okay, that's the first strategy. Okay, let's just remind ourselves what we're trying to do. That the strategy, the first set of strategy is to express our equation of motion in the new dynamical variables. So basically, in terms of delta. All right. Now we have done the first step. The second step is to what we call linearize the equation of motion, or basically in the words of Zhuzheng in the first lecture, let's try to tele-expand in delta or the new dynamical variable, all right, to linear order. So basically, uh, if you remember, sine x is basically the Taylor expansion is basically equals to x minus x to the cube over third plus blah blah blah. Cosine x is equals to 1 minus squared divided 2 plus blah 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 blah. All right. We'll just keep up to the first term. Okay, in the Taylor expansion. Okay, or some of you may know this as the small angle approximation. All right. In this case, the small thing that we're trying to expand are the deltas. Okay. The small thing we're trying to expand are the deltas. Okay, because we're thinking that, like if you think about this physical system again, where we have the new equilibrium point. Okay, but the beats started at some position that's not too far away. Okay, that's not too far away from the equilibrium point. So we have some, we say that the displacement of the beat from the equilibrium point is not that big. All right, so we can use that expansion for a small delta. Okay. So the equation of motion is basically, the first thing we can do, this one, we have sine theta EQ, cosine delta. This is basically 1. And sine of delta is basically just delta. So basically, for the first half, we have sine theta EQ times 1 plus cosine theta EQ times delta. All right. And then the next half, we have, uh, okay, omega squared. Okay, let's zoom out. Omega squared times cosine delta theta EQ. Cosine delta is 1 minus sine theta EQ delta. Okay, minus omega c squared. So this is our equation of motion, which is being linearized in delta. So what do I mean by linearized? Now you see that the highest power of delta, there's only two powers of delta here, okay? There are terms, okay? There are terms like these that are only proportional to delta to the 0, or which are, like are constant in delta. And there are terms that basically is delta to the first power, and there's nothing else. Okay, there's only delta to the 0 power and delta to the first power. And this is what I mean by, when we try to see the dynamics of the physical system near its equilibrium point, what we try to do is just, try to perturb the system, or try to linearize the equation of motion such that, the only powers of the new dynamical variable, the displacement from equilibrium, is only of the 0th power and the first power. Okay. And like here is already to the first power. Okay. So let's try to see what happens. Okay. Let's group it by delta 0, the 0th power, and plus delta to the 1 power. So maybe I'll use delta here, and then plus, sorry, delta to the 0 power, and then delta to the first power. Okay, for delta 0 power, we have sine theta EQ plus omega squared cosine theta EQ minus omega c squared. Sorry, this should be sorry, sine theta EQ. Maybe I'll change these. Oh, sorry. Maybe I'll change this to a square bracket. Okay, so we have sine theta EQ times omega squared cosine theta EQ minus omega c squared. And then for delta 1, we have cosine theta EQ times omega squared minus omega squared sine theta EQ uh, minus omega c squared. That's correct. Uh, yeah, I think that's sorry. Is that correct? Okay, yeah. Wait, something's wrong. Okay, yeah. It's correct, I think. All right. So basically, that would give you delta squared. Oh, yeah. Sorry. Yeah. 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 So this is already, sorry. Yeah. Thanks, Zidane, for. Okay. So basically, sorry. So, uh, we need to, yeah, sorry, because I haven't been clear. I think that is right. Okay. So let's be clear. So this already has some delta to the first power, and this is all multiplied by the delta to the first power. So what you should only have is this thing so it should be this. Okay, the terms here should be uh proportional to delta. Okay, so one delta is over here, so this should be cosine theta EQ, and then multiplied by things in the square bracket that does not have any delta. So basically it's multiplied by omega squared cosine theta EQ minus omega c squared. So these are the red ones. Okay. So these things multiplied by this term give you only one delta. And then there's another term, which is this term, that can be multiplied by sine theta EQ, because this also only have one delta. Okay. So this must be plus, oh sorry, it's minus sine theta EQ, sine squared theta EQ. Okay. Sorry, if there's questions, please ask, because I don't know how clear that was. So this is basically green part. Okay. So basically this is yeah. And also, yeah. And also there's gonna be a term that's, like delta squared, which is basically cosine theta EQ minus, which is basically these two terms multiplied together. But basically this is because we are linearizing the equations, we only want to keep terms that up to 0 and 1. So basically we say that this can be ignored, neglected. Okay, right? So basically this is our new equation of motion. Okay, so let's analyze this to see what we actually get in the end, right? So basically if we look at so let's pause a bit and think about what the equation of motion here tells us. Okay, so the equation of motion for delta is now arranged uh in how small they are. Okay, because if we remember, if we established at the beginning, because this is just a small displacement from the equilibrium angle, so this is something that is small. Okay, so for example, delta, if you want to have a sense of numbers, delta may be like 0.1. For example, this is considered small. Then delta squared, okay, so this is delta to the let's say if delta to the 1 is 0.1, right? Then delta squared is 0.01. And then, for example, delta 0 is, just 1. And then, things get way, way smaller as you go up. So doing this linearizing thing, the reason why we keep up to delta, only delta to the one, is because everything else is going to be very, very small, and then we just neglect it. Okay? This is why we neglect this term over here. This is why we neglect this. And because this thing is big and this thing is small, what we can do is to just, um, analyze things in terms of smallness of delta. Okay, so we analyze powers, like the coefficients of the powers of delta separately. Okay, and remember this left-hand side, is actually delta to the one with two dots. Okay, so at zeroth order, the left-hand side is actually zero. Okay, so basically delta zero sine theta eq omega squared cosine theta eq minus omega c squared is zero. What this basically tells us is that, cosine either sine theta eq is zero or cosine theta eq equals to omega c squared divided by omega squared, which is basically just, the equilibrium conditions that we had at the very beginning. Okay, so let's look back at the very beginning when we have the equilibrium points. This is what we had. This is basically we're saying that theta double dot is equal to zero. Then either sine theta is zero or cosine theta equals to omega c squared divided by omega squared. This is basically just regaining the equilibrium conditions that we have. Okay. Okay. So this is at uh delta zero order. Now the fun thing comes at delta to one order, because at delta to the one order, the left-hand side is non-vanishing. Okay, it's not zero. Okay, so we have delta one to delta to the first power double dot equals to delta one multiplied by this entire thing. Okay, so we have something interesting going on. Okay, so um, if you look here, we see that sine theta eq omega squared cosine theta eq minus omega c squared is exactly this thing over here, and this basically is zero. It's basically zero. All right. So this equation of motion simplifies to uh this thing. Sorry, let's write it in a more informative way. This is negative sine squared theta eq multiplied by delta to the one. Okay, and this is the equation of motion. Uh, this is the equation of motion for the displacement from the equilibrium point. Okay, so basically, let's summarize what we have done. So basically, what we have done here is basically step 3 of what I wanted to write, but I forgot. Basically, step 3 is to, analyze power by power of delta. Okay, so the question is, so basically, to answer the question, what are the dynamics away from an equilibrium point? There are three main steps that you should do. The first thing is basically, what did I say? The first step is define a new dynamical variable or coordinate. So from an equilibrium point xeq, let's use red, xeq. So the first thing to do is to define a new dynamical variable or coordinate. Okay, which is basically saying that the position, okay, you can define as EQ plus some deviation delta or displacement delta from the equilibrium point. Okay. The second thing to do is rewrite equation of motion in terms of xeq and delta. Oh, I think this was the fourth thing actually, because the third thing to do is to linearize, or basically keeping powers of delta to the 0, delta to the 1. And the fourth thing is, analyze power by power of delta. And basically, it always will be the thing that delta to the 0 gives you the equilibrium conditions. And delta to the 1 will give you something of the sort that delta double dot must be equal to some uh some some f of x equilibrium. As you can see at this point, maybe I should write it a bit like this. Oops. It gives you something that is in terms of the equilibrium position, and then times delta. Okay, so this is what you do for dynamics away from an equilibrium point. Okay, all right. So that's a general idea of how do you analyze, dynamics away from an equilibrium point. You have no idea what this has to do with waves and oscillation up to now, but this is, as I said, the informal title is analysis of dynamic systems, and this is the dynamics away from an equilibrium point. If you're displaced from an equilibrium point. Okay. So up until now, is there any questions? Okay. All right. If there are no questions, so all right, so we'll move on. Okay. So we'll take a better look at what does it mean that look at this equation. Okay. Look at the equation that we get for the bead. Okay. So for the equation of the bead, what we get was delta double dot equals to negative sine squared theta eq times delta. Okay. So uh let let for let's rewrite for let's say omega, this thing must be is equal to some omega, just for this is definition. Okay, let's define this thing so that we can write it in a little bit more convenient form. Okay, and what we're trying to do, okay, for the next hour and so is gonna try to analyze what this equation of motion for the displacement from the equilibrium point is trying to tell us. Okay, so this is the equation of motion for small displacements. Equation of motion for small displacements that we got. Okay, and let's try to solve it. I don't know if Jason has solved this during the first lecture on, because I saw the timetable it said had differential equations, but I didn't know. Doesn't have do they know how to solve this equation? If not, I will. Don't think so. Okay, cool. No worries. Okay, so there are many ways to solve this differential equation. Okay, I will go on a different route on why on solving this, such that it is, it's helpful and uh to for discussion. So let's look at this equation. So let's move this thing to the left-hand side such that this equation looks like this. Okay, is delta double dot plus omega squared delta equals 0. Okay, now we're gonna, or let's even write it even a little bit more symbolically. So this is the second time derivative acting on delta. plus omega squared delta equals 0. Okay. So let's call this session how to solve this question. How to solve. Okay. So I will hereby give a trick on solving this. Okay. The trick is basically, saying that this thing, uh, let's factorize delta out of the equation above. Okay. Let's say that this is legal to do. Okay. And if you squint your eyes a little bit more closely, you can remember from your high school that a squared minus b squared is equals to a plus b, a minus b. All right. Uh, so an a squared plus b squared is basically just a squared minus negative b squared. So this can be written as a plus negative b squared. Yeah, I wasn't writing something wrong. Okay. A plus square root of negative b, a minus square root of negative b. Okay. Oh, sorry. This is square root of minus b squared. Okay. All right. So this is what you remember uh from high school. Sorry, what did I write wrong? A minus, oh, sorry. Okay, let's rewrite this. This is a squared minus negative b squared. And then this is equals to a plus square root of minus b. Yes. Okay, this is right. A minus square root of minus b. Okay. And I again don't know if Susan told you about complex numbers, but maybe and I don't know how current high school teachers teach you, but this is basically a plus ib, a minus ib, where I is equals to square root of minus 1. Okay. Okay, hoorah. Okay, this is a trick that we can use. So basically, what we're trying to do is from this equation, we'll try to factorize it again, such that to break into a smaller chunk, such that this thing I can write as d over dt plus I omega, d over dt minus I omega, delta is equal to 0. How does the delta get separated from the derivative? Well, basically, this is we well this well it's already separated, right? Because like this is the time derivative acting on delta, right? So if you have a function f of x, the derivative of f of x, well, like this thing, like like acting on f is basically just like a of f is a acting of x such that it's multiplying, d of dt is multiplying by f such that it takes derivative. So as I said, like let's just say that this is legal to factorize this out. Okay. And let's work from there. Okay. So the reason why I wanted to do this is because this is less like like factoring out this thing makes a little bit more sense than the other ways people solve this equation. There's also some magic, but it's not that much magic. Well, you could also you could rewrite this, you could multiply this equation, you know and get the uh get the original equation. Okay. There's also another way to factorize this equation, such that you get d over dt minus I omega and d over dt plus I omega, delta equals 0. So you actually have these two equations. But okay, so what now? Okay, so how can this equation be solved? This equation can be solved. Equations can be solved if, d over dt minus I omega delta is 0. or d over dt plus I omega delta equal to 0. Okay? So either this thing is 0, so whatever here, whatever acts upon from the whatever this thing acts upon it is still 0, or maybe this thing is 0. Okay? Maybe this is 0, or maybe this is 0. Okay? There are two possible solutions. And these two equations you can solve. Okay? This is basically d over dt delta equals to I omega delta. All right, you know how to solve this? This basically tells you that d delta over delta is equals to I omega dt. And integrating this out, uh, can anyone tell me what the left-hand side integrates to? Yes, it's basically ln of delta, the natural log of delta. I don't like this color. Is equals to I omega t plus a constant. Okay, or in other words, if you exponentiate this thing, you can get delta is equals to exponential I omega t plus c, or this is exponential I omega t exponential c, or I can define it as a e I omega t. Same things happen for this equation. You can know that this will give you delta is equals to uh let's call it b because it can be something different, exponential negative I omega t, because what changed is the sign of omega. Okay, so both of these things are solutions to the equation of motion. So solution to delta double dot plus omega squared delta is equal to 0 is basically delta is a e I omega t. Okay, this is one solution, and the other possible solution is negative I omega t. The reason that we can add these things together is because if one thing solves the equation of motion, the second one solve it. So this can be a homework. Check that if a e I omega t, so this can be a homework that you can do. And delta equal b e negative I omega t solves this. This is delta 1, this is delta 2. Delta equals to delta 1 plus delta 2 solves it too. So you can check. Okay. But basically, this is basically uh the solution to this equation of motion. Okay. So anyone here can tell me what does this mean? What is this? Okay. Uh, what what are the implications of this? Like how does delta change with time? This is a complex number, so how can you what actually is the thing that's happening? Okay, because we have complex numbers here. Yes, I can change it to cosines and sines. Okay, so the way to understand this is because remember these looks like complex number and a and b. So I might stress that note a and b are complex numbers. Okay, so uh, but delta, remember this is some x. So for our purposes, is basically an angle which is real minus the equilibrium position angle, which is also real. So delta is real. Okay, so that means that you can't have just random A's and B's. Okay, so the combination of A and B's must give a real delta. So the first thing you might know that what does it mean for delta to be real? So like for example, 5 is real. What does it mean for 5 to be real instead of complex? or imaginary. Basically, 5 minus the complex conjugate of 5 is equals to 5 minus 5 is 0. So basically, for delta to be real, what it tells you is that delta minus the complex conjugate. So I hope you know what complex conjugates means. So complex conjugate means turning i's to negative of i's. Okay, so this is what a complex conjugate mean. So delta minus delta star is 0. Or basically it equals, let's just say that it's equal to its complex conjugate, which means that delta minus delta star is 0. Okay, so delta is equals to A E I omega t plus B E negative I omega t minus a complex conjugate E negative I omega t. Okay, turns I to minus I, and these are complex, so they also get conjugated, plus B E I omega t is 0. Well, basically what happens is A minus A complex E omega t plus, sorry, A minus B star. Okay, so for exponential I omega t, these are the ones that we have. And for negative I omega t, these are the ones that we have. So we have A minus B star for E I omega t, and B minus A star, E negative I omega t is 0. All right. Uh, so in other words, so this is the green part. We have a condition that A must equal to B star. Okay. This is the condition for real delta. And what this gives is basically that our motion is basically A exponential I omega t plus a complex conjugate E omega t. This is the first thing that we have. And then, if you remember, the exponential I theta from Euler, so this is basically from Euler's formula. The exponential I theta is equals to cosine of theta plus I sine of theta. Then delta t must be equal to A cosine of theta plus IA sine of theta minus A complex conjugate cosine of negative theta. Oh, sorry, the theta here is omega t. So let's write that down. Right, omega t minus the minus sign here, minus omega t minus sorry, this is plus, right? This should be plus a star cosine minus omega t plus I a star sine negative omega t. Okay, or it's a plus a star cosine omega t minus I a, sorry, plus I a minus a star sine omega t. Okay, and if a is equals to some real part of a plus I imaginary part of a, basically this gives you that a plus a star is equals to 2 times real of a part, the real part of a cosine omega t, which is real. Again, this is real. Cosines are real. The real part of a is real. Plus I a minus a star. So a star is equals to real part of a minus I imaginary part of a. And a minus a star is basically 2 times I of the imaginary part of A sine omega t. And this is equals to 2 times real part of A cosine omega t minus 2 times imaginary part of A sine omega t. All right. So what happens is that, remember what we're trying to solve was what happened to the beat when there's when it is, when the uh when the when the when the equilibrium point is shifted because the hoop changes its rotation frequency, is basically that, this delta over here starts to oscillate in terms of sines and cosines, okay? So if you plug in, so this you can try to do this, you can try to solve the boundary conditions. So the boundary conditions is that initially at t equals 0, that delta of 0 was, was theta eq minus theta of 0. And then initially there was no velocity, okay? There was no velocity, sorry. Initially that theta dot at time equals 0 is 0. So that delta dot of 0 is 0. You can try to solve this and basically say that delta of t must be equal to theta equilibrium minus theta of start cosine omega t, and cosine omega t, omega is basically, sine theta eq, okay, times t. So what happens is that this thing starts oscillating back and forth, like this from the equilibrium point, and just, continue to do this. It just keeps on oscillating, uh, just back and fro, back through its equilibrium point. Okay, and this is why, and then you see that this is some oscillations. Okay, so let's remember what we have done. Okay, we didn't start out thinking about springs and blocks, pulled by springs, but we never talked about pendulum and such. We just analyzed a very simple system saying that what's the dynamics of a bead uh, on a rotating loop when the angular velocity of the loop is changed. Okay, it's just a dynamics when a change in the external system results in a change of an equilibrium point, and there's a small displacement of an equilibrium point basically gives you these oscillations uh, of the sort. So basically, the equations of the sort that delta uh, these things basically tells you that these are simple harmonic oscillators. Okay, this is completely equivalent. This is completely equivalent if you just have a, maybe I'll draw it horizontally, so no gravity. So this is identical to try to displace. So for example, if this box will have some equilibrium point and then you push it away, then it starts to oscillate, then basically you say that, the mx is equals to uh negative k of x, okay, or x double dot plus k over mx equals 0. It's the same simple harmonic oscillator equation, and it comes out just, it comes out just naturally just by, seeing that how things are changed, what the dynamics are when you displace the system out of its equilibrium. Okay? So, and this is very ubiquitous, okay? It appears everywhere in nature. So how can we see that it appears everywhere in nature, okay? So basically, give me any physical system. It can be, a bead on a rotating hoop. It could be, a block with a spring. It can even be, fox eating rabbits in nature, okay? So give me any physical system. What you always write down is an equation of motion, okay? An equation of motion is basically that the change of, some dynamical variable x. This dynamical variable can be really a coordinate system, like the theta. So this is a dynamical variable. For example, it could be theta, okay? it can be the theta, it can be some x for a block, it can be a number of rabbits, you know, in a jungle. All right, it can be anything that is changing with respect to time. Okay, and then this is anything that's of this form is called an equation of motion. Okay, and equation of motion is basically saying that what is the change of the dynamical variable with respect to time. Okay, and it's going to be a function of external variables, and of course, like the dynamical variable itself. So these are equation of motion. Equation of motions are not just things that like F equals to ma. It can be anything that's dynamical in this sense. All right, and if you do the steps 1, 2, 3, 4 as we said before. So step one, new dynamical variable. So let's say that x goes to x equilibrium. That's an equilibrium point. Uh, uh, okay. So basically, if you have an equilibrium, displace it from the equilibrium point. So basically, what you get is the equation of motion becomes delta double dot equals to f x eq plus delta. Okay. The second thing is to linearize. So using Taylor's equation, Taylor's formula. So Taylor tells you that f x plus a. Uh, maybe I should use something different. Taylor expand. So f let's consist f uh a plus. Okay, okay. Let's just write it like this. Must be equals to f of x naught plus delta is equals to f x naught if I expand around x of eq, the equilibrium point. This is fx naught plus f prime, the derivative of vector is a vector x naught plus delta times delta, f the second derivative of x naught divided by 2 delta squared plus blah blah blah. And because I linearize, I only keep out to delta to the first power. Again, this is delta to the 0 power, this is delta to 1 power. Okay, so basically I always have delta double dot is equals to f x eq delta to 0 plus f prime x eq delta. Okay. The third part, analyze equation of motion. Analyze power by power. Was this so? What was my recipe? Okay, I rewritten EOM in terms of, yeah. So I rewrite. Sorry. This is the second part. This is rewrite. Okay, this is third part. The fourth part is analyze power by power. So at delta to 0, f x eq is equal to 0. Well, this is basically equilibrium analysis, because even if we look at the equation of motion, when x double dot is equal to 0, f at this point is equal to 0, x eq. So basically this tells you, when x double dot is 0, that you can find an equilibrium point such that the fx is equal to 0. Okay, so that is the delta 0 part, and the delta 1 part basically give you delta double dot is equals to f prime x of eq delta, or this is instead f prime x eq of delta. All right. So here's an interesting thing. The simple harmonic oscillator equation is delta double dot, okay, plus omega squared delta is equal to 0, right? So there are two things. So it's a little bit different here, okay? So in the most general case for equation of motion, this is actually delta double dot minus f prime x eq delta. Okay, so there are two situations here, okay? So if f prime of x eq is uh smaller than zero, okay, then basically I can rewrite as I can define, you know, uh f prime of x eq equals to negative omega squared, okay, because this is something that's squared, this positive, and then minus, then this is smaller than zero. Then I know that delta t must be equal to some sine oscillations or plus cosine oscillation, okay, that where a and b are real numbers, that in this case a and b are real numbers and they are completely fixed by your boundary conditions, okay. uh in the other case, otherwise, if f prime of x eq is larger than zero, what happens? Okay, what happens? Then I can define f prime of x eq. Let's not use negative omega squared. Let's use equals to lambda squared. That's larger than zero. Okay, so we have delta. This must be equals to lambda squared delta equals to zero. Sorry, minus lambda squared delta equals zero. Okay. Can anyone tell me like what are the solutions to this equation of motion? What is delta as a function of time? Non-imaginary exponential, okay? So basically it can be some a again, okay, if you're not sure, this can be easily simplified to d over dt minus lambda d over dt plus lambda, acting on delta equals zero, and also, like d over dt plus lambda d over dt minus lambda equals. Okay, now you can solve this equation of motion, and then you see that delta over t must be equal to a exponential lambda over t plus b exponential negative lambda over t. Okay, so depending on your boundary conditions, okay, this depends on the boundary conditions. You either get, something, uh, that's either growing with time exponentially, uh, or you start with, or you get something that decays at time exponentially. Okay, so these are non-oscillating solutions, and what this means is that, for most of the time, for example, so let's consider a case that, at t equals zero, delta equals to some, to some initial value, okay, and delta dot is zero. And what you get is delta t is equals to uh sorry, delta equals to zero, delta t equals to zero is equals to a plus b, and delta dot at time equals zero is equals to lambda a minus b. Okay, and this basically tells you that, a equals to b. Is that correct? T minus lambda. Yes. And basically this tells you that, uh a must be equal to x naught divided by 2. So basically what you get is delta t must be equal to x naught divided by 2 e lambda t minus e negative lambda t. There's always gonna be a part that's gonna go exponentially far away from delta. exponentially far away from delta. And what that reminds you is basically tells you that, like in some systems, unlike the bead on rotating hoop, so in the bead on rotating hoop, remember that, this guy over here just oscillates around the equilibrium position. Okay? It just oscillates around the equilibrium position. But in some cases, if you just displace it away from the equilibrium point, what happens is not that it oscillates. Okay, what happens is that it just basically just goes exponentially far away. Okay, because this thing at large t is basically just exponential lambda t, because this is died down to almost zero, and basically this thing just go exponentially far away from the equilibrium point. And basically this tells you that, for f prime of xq smaller than zero, this thing is a stable equilibrium, and f prime of xq larger than zero, this is an unstable equilibrium. Okay? Some of you might, so for example, so for some of you, this might be more keen to, understanding potentials and looking at, uh, so remember, so for mechanical systems, sometimes you have equation motion that looks like, mx double dot might be equal to force of x. Okay, and if it's conservative, so for conservative forces, you can always write down in terms of the negative of uh uh a uh a potential. So this must be negative du over dx. This basically tells you that if du dx, okay, is uh negative du dx is smaller than zero, sorry, negative of the second derivative is lower than zero, this is a stable equilibrium. And negative of d to u dx squared is larger than zero. This is an unstable equilibrium in terms of the potentials, okay? So these things are basically concave potentials. These are basically convex potentials, okay? All right. Any questions? So that's basically oscillations and how to think about oscillations in a more general framework. Any questions? Okay. All right. Okay. So some caveats I want to make sure. So for small displacements, for actually really small displacements, a stable equilibrium is always stable without uh if no changes in external variables. What do I mean is that, if you just displace the system from a stable equilibrium point without changing anything else except for the equilibrium point, except for, just making a displacement from the equilibrium point, then it's always stable. Uh, okay, that's not, sorry, it's the other way around. Sorry. Sorry. For less than one, unstable equilibrium is always unstable. Sorry. Unstable equilibrium is always unstable if no changes in external variables. Stable equilibrium can be unstable uh due to other stuff. I'm not gonna I won't have time to go into what these other stuff are, but keep that in mind that if you have some very nonlinear behavior, you can start making stable equilibrium unstable. Um, yeah, you can it can be unstable due to nonlinearities in the in the potential and in the forces and in the equation motions. Okay. All right. So is there any questions with this? So these are the caveats. So what we have been doing is only linear perturbation theory. Okay. So everything is only uh stable and unstable equilibrium, and all these things are only done in stable equilibrium. Uh, okay. So yeah, if there's no question, I'm gonna go to part two. So that was part one. So let's just say that was part one. Part one was basically dynamics in 1 degree of freedom. What I meant was 1 degree of freedom was that, what we was thinking was, a box with a spring and it only can move in X and Y directions. And for example, in our worked out example, we would think of a bead on a loop, in the rotating loop. And this bead only was able to move in one direction. It's basically around the circle of the loop. Okay, these are dynamics in 1 degree of freedom. Okay, in some cases, you have, dynamics in 2 degrees of freedom or more. Okay, but we'll just deal with two in the meantime. Okay, so let's see how can we deal with dynamics and more 2 degrees of freedom and more. And how it complicate things and make also very interesting phenomena happens. Okay, so okay, we start with so for 1 degree of freedom, you guys know about boxes and springs, so we consider something a little bit more different to show you the how general oscillations appear in nature. But in 2 degrees of freedom, maybe it's better to stick with boxes and springs. Okay, so imagine we will have a frictionless table. Again, I like to lead with examples, so this is a frictionless table. Okay, and then for example, let's have a board over here and a board over here. Okay. And on these two boards, let's have springs connected to some block, okay, to a block of mass, okay? Okay. So yeah, so this is the box, okay? So the box can move, on this X and Y plane on the table, okay, in any position it can. So for example, you can move to here, okay? So the question is, if you just displace the box randomly by displacement vector, some displacement vector x and y from its equilibrium point, what happens? Okay, this is an extension of the problem above, right? In the question above, we have, 1 degree of freedom. And the box only moves in one direction, the bead only moves along the circle. Now we have, a little bit more flexibility. So the question is, what do we do? Okay, the first thing that you do to analyze a dynamical system is write down the equation of motions. Okay. Okay, so let's say that this block has mass m, the springs has the springs have, spring constant k, and then, when relaxed, the springs have natural length, L naught. Okay. Uh, all right. So there's no way I can finish a lecture of waves and oscillations if I analyze the equation of motion of every system. So this is your homework. I'll put it on the handouts tomorrow when I send it to the WhatsApp group. But the homework is try to okay, what are the EOMs? What's the equation of motion for the system? I'm gonna write it down, and you need to make sure it's correct. So let's EOM and linearize in X and Y. Okay. Uh, so what are the equation of motions and how do you linearize that? I'm gonna look at my notes. So if I can find okay. So the equation motions. are basically uh x double dot is equals to uh negative 2 minus epsilon of x plus epsilon of y. Y double dot is equals to negative 2 minus epsilon of y plus epsilon of x. So uh so basically with respect to so basically this is basically these 2 points are along the diagonal. So from this, if we put the equilibrium position at 0 0, so let's say the equilibrium position of the blocks is at 0 0, then this pivot is at a minus a. So the x-axis is defined here, and the y-axis is defined like this. Okay, so this is at a minus a, and this guy is at minus a. Okay, what you get for the equation of motion is basically something that looks like this, uh, where sorry, there's a k over here. There's a m x double dot and a k. Sorry, these are kx plus epsilon ky, ky plus epsilon kx. Okay. So here are the equation. So here are the equation of motion, where epsilon is equals to L naught square root of 2 divided by 2a. That's a very lousy way of writing that. Let's write it like this. I think that is right. Okay. So where epsilon is this thing. Okay. So you could try to prove this. Okay. This is a very nice exercise to make sure that you know what was happening in the first question, in the first part, in the x and y directions, uh, and just to work things out. Okay. So, okay. This is a problem, right? Because like if we have so the question here is that, if we look at the x directions, the oscillations in this looks like this part over here. The first part looks like an oscillation in x. The third part looks like an oscillation in y, like a simple harmonic oscillator. But it's not that simple because they are coupled together. So the equation of motion in terms of x is coupled to uh the uh the displacement in the y direction, and the equation of motion in the y direction is coupled to the displacement in the x direction. So this is not that easy. These are what we call coupled equation of motions. So these are what we call coupled equation of motions. And like this is not a very weird system. This is just a system of springs and blocks uh, just aligned along the diagonal axis. Okay, so this is not something that's very that's very like arbitrary, right? Like this is you can find this on a lab table. Okay, so these are coupled equation motions. Um, so the question is, how do we solve this equation of motions? Okay, so I'm gonna give you yeah, so basically these are couple equation of motion. I'm gonna give you, two ways of solving this. There are also many ways of solving this, but I'm gonna give you two ways of solving this. Uh the first of so there are one the first one is, by guessing. Oh, my physical insight, okay? And the second way of doing this is by, like brainless math. Okay. So I think it's always nice to look at the physical insight a little bit more. So if we look at this system, like you can okay, a physical insight. Like what do you think was the problem what was the thing that gave us this very how do you say very nasty equation of motions. Does anyone have an idea of why this is the case? So example, if we just displace the block in the x direction, this thing will have you will this will also this guy will also oscillate in the y direction. And if I displace it in the y direction, it will also move in the x direction because any displacement in x and y will source y and x motion. So any displacement in x and y will source this motion in y and x, so in the different ways. So springs exert force along the spring. It's sorry, can you elaborate? So the question was why do we end up with these very nasty coupled equation motions? So the physical one of the physical insight, so along the line, okay. So one of the insights is that, like if we just think about so let's think about physical insights. If we just think about, a normal block just squeezed between two walls. And there's also a y direction here, okay? So there's a y direction here, but just like this. If I just displace the block in, the x direction, nothing will happen. The block will just, like will just oscillate around the x direction. And if I just displace along the y direction, the block would just displace along the y direction if I did this setup, okay? So one of the reasons is that, this is a very bad coordinate system that we use. What the nice coordinate system would do, set our x-axis and y-axis along this directions. And then, the oscillations along the diagonal, the x plus y diagonal will be completely unrelated to the oscillations in the x minus y diagonal. So the physical insight is that, we have chose bad coordinates. We should have used coordinates x plus y and x minus y instead. So this is a diagonal. This is this diagonal over here, and this is this diagonal over here. Okay. So yeah, so let's remedy this. Okay, by looking at what can we what can we uh so basically, like, how can we remedy this at the level of the equation of motion? Because we have gone into, all this trouble of writing these down. We don't want to, rewrite everything, uh redo the, linearization, redefine the axis, redo the linearization. Like, these are very trouble things to do. So how can we remedy this in terms of the couple equation of motions? The first thing that you can do is, you know, x plus y, x minus y. So why don't we just add them up? So let's say this is 1, this is 2. So if we add up the two, we get m x plus y double dot equals to negative 2 minus epsilon k x plus y plus epsilon k x plus y. And if we define, a new coordinate, let's call it c plus is equals to x plus y, then c plus double dot equals to x double dot plus y double dot. Then we can see, then we have an equation of motion that's, as you can tell, is decoupled. So this gives me 2 minus epsilon k c plus epsilon k c plus. Or in other words, this is what is this? This is plus, so this is minus 2 1 minus epsilon k c plus. Or I could just write, c plus is equals to this times omega squared, where omega squared is equals to k over m. Okay, and now we see that, this was our intuition, that if we just, change our coordinate system, like, the motion along this diagonal has nothing to do with the motion along the other diagonal, as we can see, because if we do 1 minus 2 instead, okay, we can see the same thing, that m c minus double dot is equals to negative 2 minus epsilon k to c minus, and then plus epsilon k to c minus, okay, where c minus is equal to x minus y. And then we can see that c minus is equals to negative 2k, negative 2 omega squared c minus, okay, because this is plus epsilon, uh, sorry, this is a minus sign, okay? This is plus epsilon, this is minus epsilon, because we have y minus x, okay? So the epsilon cancels out, and this is what we have, okay? And again, this is something that's only oscillating in along the negative diagonal and has nothing to do with the oscillation in the x plus y diagonal. Okay, so we have what we have done is decoupled the equation of motions into two independent degrees of freedom. And something other to note is that, like this is a very neat system, as in, uh, what you can see is that for C plus and C minus, they have different oscillating frequencies. The oscillating frequencies for the first one is equals to, square root 2, 1 minus epsilon omega, while the second one is, sorry, it's just square root of 2 omega. They have different oscillating frequencies. And for 2 degrees of freedom, you get two oscillating frequencies. And if you have three degrees of freedom, you get three. But this is basically, the when I say three, you can have three, but two. It might be two of the same. But for example, like these can be the same if epsilon is equals to minus one. In this case, it's not possible, but it may be possible. Okay. So this is, from physical insight, you know that, sometimes this basically you just chosen a very bad way of understanding the system. And if you chose a better way of understanding the system, you get equation motions that are decoupled. And what happens is that, if I just displace this block, so for example, like this is equilibrium position. If I just displace this box like this, what happens is that, this block would, this is in the displacement in the z minus direction. What happens is that, this block will just oscillate around the equilibrium point in this fashion. Okay, it will just oscillate along this diagonal. And if I just, if I displace it, purely along, this direction, then the block would just oscillate around this uh equilibrium position in this direction. Okay, and this is along this C plus direction. All right, are there any questions? So one reason we get coupled equation motions is basically that we have chose a very bad way of describing the system. All right. So this is one way of how to analyze coupled equation of motions and coupled oscillators. Um, I want to spend some time to talk about the second way, which is brainless math. Sometimes not as easy to see like how you can add and subtract equation of motion such that you gain more insight into physics. But like we can always make do with brainless math. So if you're more math oriented, uh this might be helpful. And sometimes it's not easy to see. One thing you can see is that, okay, has some y in it. So how can we eliminate the y? Okay, we can eliminate the y because we have equation of motion for y double dot. So, one brainless thing to do. So, for simplicity, uh, okay. So I'll rewrite this equation of motion as, uh, for simplicity, I will call this omega k divided by m to be omega squared. So I will have like this will be just omega squared y, omega squared x. Uh, okay. And so basically one thing to do is just, differentiate one, two times with respect to time to get x, 4 dots equals to -2 minus epsilon omega squared x double dot plus epsilon omega squared y double dot. And then you can now substitute in 2, you know, to get, -2 minus epsilon omega squared x double dot. Again, this is really brainless maths. Uh, and substitute this in to get -2 minus epsilon omega squared y plus epsilon omega squared x. And this is equal to -2 minus epsilon omega squared x double dot. Let's take the x component. This is plus epsilon squared omega to the fourth x. All right. Uh, minus, again, we have omega squared y here, which you can substitute in equation 1. Okay. So in the red arrow, you substitute in equation 2. In the orange arrow, you can substitute in equation y for omega squared y. Okay, for epsilon omega squared y. And then you have, okay, so this is -2 minus epsilon omega squared. And then so these are these guys. -2 minus epsilon omega squared. And then epsilon omega squared y, you have from here x double dot minus of plus 2 minus epsilon omega squared x. Okay, and then you get an equation of motion that x to the 4th dot is equals to -2 minus epsilon omega squared x double dot. Okay, there's 2 of them, right? And then for the x part, you get plus epsilon squared plus 2 minus epsilon, minus 2 minus epsilon squared omega squared x. And if you do the maths, this is omega squared x double dot plus, this is 4, 1 minus epsilon omega squared x. So you can sort of now. So I think there's a typo here somewhere. There's a omega to the 4th somewhere. I think it's omega 4th is here. Okay. Yeah, this should be it. Yeah. Okay. Or is it 2 minus 1 minus 9? Okay, let me check my notes. Da-da. Should be minus or 1 minus epsilon. Yes. Yeah, I think that should be correct. All right. So, one thing I can do now is let uh so for sake of notation, let's say d over dt. Let's say this is just d. Okay, let's define notation. Okay, so if we rearrange this, we have, d to the 4th on x minus 2, plus 2 minus epsilon omega squared d to the squared minus, plus 4, 1 minus epsilon omega 4th uh There's no D here. And this entire thing is actually acting on X to give you 0. Okay? So one fun thing to do is, to do our same trick again and try to, uh try to try to factorize this differential operator over here. So one thing you can find is that, you can change this, you can factorize this into d squared minus uh I think it's 2 omega squared, and d squared minus uh 2 1 minus epsilon omega squared x equals 0. Let's see if this is correct. Maybe it's plus. Uh, yeah, I think this is correct. Okay. And all right, so uh basically then you get, you can factorize again. So that is d plus I square root 2 omega, d minus I square root 2 omega, d plus square root 2 1 minus epsilon omega, d minus, sorry, there's an I square root 2 1 minus I epsilon omega, x equals 0. And again, this is again of the sort of, like these four, this four square brackets, you can shuffle them together, and each of them needs to solve the equation such that they give x equals 0. So basically, x of t, sorry, this is not x. Yes, this was x, okay. X of t uh will be equal to, some a e, I square root 2 omega t plus b e negative I root 2 omega t plus c e uh I square root 2 omega t plus d e negative I, sorry, this is 1 minus epsilon square root 2 1 minus epsilon, oops, omega t plus d e I 2 1 minus e omega t. All right. So, what you see here, like, is basically, just a brute force way of solving the equation of motion. And like for now, like in this case, you can know like there's some other insight that comes into here, right? So we know that these equations are basically oscillations, okay, of different frequencies that corresponds to, the oscillation frequencies that we have found above in the, physical insight question, where we have omega plus being the frequency that you have by oscillating in this diagonal, in the x plus y diagonal, and square root of 2 of omega is the, frequency that you were oscillating in the x minus y diagonal. So basically what you have here, you know first of all, using brute force and substitution and, factorization, you could basically you could basically find that, the oscillation in x. So remember what we're doing here. We're still using the xy coordinate such that uh we're using the xy coordinate like this, and saying that, okay, how can we understand, a motion if it's just displaced in x. Okay, so this is the equilibrium position and this is only displaced in x. Okay, or if it displays anywhere else and I just try to understand how it was oscillating in terms of the x direction. Basically, this gives us one way of understanding it. So basically, this is saying that the oscillation is x is basically a combination, or in some words, a linear superposition or just a superposition, of the theta minus modes. So these are theta minuses, and these are theta pluses. Sorry, Z pluses. It's a combination. Is a superposition of C minus of T plus C plus of T. Okay, so things that so you have two degrees of freedom that oscillate at different frequencies, and if you just look at one, you just have a random displacement and it starts moving. You can see that x of t is basically a linear superposition of these two oscillating modes. So you just combine it together. Okay, it's a combination of the oscillations in the two independent directions, and you can do the same thing. You can do the same thing for y, okay? If you put, if now you have x and y, you have x, you can substitute it into this, and then you get y, and then you will find that y does something similar, something similar. It's also uh, like this, but maybe with different a, b, c's, and d's. Basically, this is just it, okay? This is just it. So any random oscillation in two degrees of freedom is just a superposition of the two independent degrees of freedom. And this is the whole principle of linear superposition, okay? Um, yeah, so that is all I have to say about oscillation in two degrees of freedom. There are two the like Yeah, so this is just it, and now you can try to solve the equation of motion by saying that, okay, what's your initial displacement, what's your initial velocities, and in the zero, you can in these, and you can substitute it in, and then you can see like you can see xt and yt is basically being this these things, and this is very fun if you eliminate t and just think of, okay, what is the path that is drawn by these x and y's drawn by this oscillator here, you find that they are something cool. I'm just gonna say it here because they're cool. They're basically what people call Lizardos curves. Okay, they're basically what people call Lizardos curves, and they look very cool. Yeah. So, and I'm gonna give you handouts tomorrow, and I will include some other system, but basically a combination of this, but using pendulums, and you can DIY a Lissajous curve pendulum drawing pendulum at home. And it's very fun. Okay, so that's what I have to say about two degrees of freedom. Any questions, perhaps? Okay. Uh, if there's no question, I have 5 more minutes, maybe 10 because we started at 10:05. So we talked about, oscillation 1 degree of freedom and couple oscillators, which occurs when you have three or more degrees of freedom. Okay, maybe I should tease a little bit more about this. So, like, this not only happens if you just, go 2D, you can think about oscillators that just like this. So in 2 degrees of freedom, you can also have, instead of that, you have two oscillators connected by strings. And the displacement from the equilibrium, let's say this is Q1, this is Q2. The displacement from the equilibrium point, okay, or delta one, delta two, is the same. Okay. These things are also harmonic oscillators, couple oscillators, right? Because you can write down equation of motions. Again, do this at home. That basically says, okay, the first block is pulled to the left if it moves. Sorry, this is Q1. And also if there's a linear Q2 minus Q1 and Q2 minus Q1, if this gets stretches, this gets pulled to the right, so it's a plus K. Okay, convince yourself this. And for the second one is something the same. If you push the second block to the right, the spring pushes back to the left. And because of Newton's third law, you know that this must be a minus sign. And like this again gives you something that's a couple equation of motion that have Q1 and Q2. The motion in Q1 is also is affected by the displacement in Q2. And the motion and cues of the second block is also depend on, the position of the first block. These are also couple equation motions that are not just because uh, you have a bad, like coordinate axis, but it's because you chose like a very non-physically motivating degrees of freedom for the displacements. As you can see, these equations are almost exactly the same as the ones we have above, so you can add and minus them together. You will find that, like you can define theta plus as q1 plus q2, and theta minus as q1 minus q2. And what it's saying is that, you can instead of saying that, uh, instead of using instead of using, the Q1 and Q2 in the individual blocks, you can use C plus and C minus. It's basically saying that, okay, either I move these two, sorry, so for example, for this guy, I can move these two by the same amount Q, okay? And then it goes, it symmetrically goes back and forth together because the middle string is not compressed or extended. Or what you can do is, do this, okay? Q minus Q. And then, uh, they are in sync antisymmetrically, okay? I'll leave this as homework for you to solve. But again, this is something that's very interesting in couple oscillators that you don't need, a 2D system to have couple oscillators. But all the physical insights are the same. The reasons that you have couple oscillators because you have chosen a very bad uh, coordinate system or choice of displacements such that the insights are not apparent. Okay. Uh, yeah. Okay. So for the last few 5 minutes now, or 7 minutes, I want to talk about systems that not with 2 degrees of freedom, 3 degrees of freedom, but systems with oscillations with like infinite degrees of freedom. Okay. Uh, So what do you mean? So let's just think about a little bit less than infinite. So let's think about the system again. So there's, like one block, two block, and there's a lot of blocks, okay? And there's a lot of blocks, just connected to each other. So there are many, many, many blocks, okay? You can write down equation of motion for the I block here. So let's this be the I block. This is the I plus one block. This is I minus one block. Again, you can write down an equation of motion for okay, let me look at my notes of how I write it. Okay. So let's say that this is Q of I. Hmm. Yeah, okay. And Q of I, Q of I plus one, Q of I minus one. So the equation of motion can be written as, for the I block, you can know that, it's the same as before. You have uh you have negative K Q. So basically you have Qi minus Qi minus one. So for this spring over here, and and it's I think it's negative two. Uh sorry. Qi plus one minus Qi. So this pushes you to the left. Okay. Yes. This pushes you to the right. This pushes you to the left. Okay. Uh, or in other words, this basically if you K Qi plus, so M divided by K of Qi is equals to Qi plus one minus two Qi minus two Qi minus one. Okay. This is what a many, 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 many degree of freedom oscillator can look like. And we can make this, like these blocks infinitely dense, so we can have a lot of blocks, a lot of blocks, a lot of blocks, and fill this entire line. So what would happen in that regime? Okay, what that would happen is that we actually we can't actually define the ith block. Instead, we need to define like where this block is along the x coordinate. So for example, the displacement of this guy over here can't be written as Q. The block, sorry, the displacement of the ith block over here cannot again be displaced by the ith position or the ith block, but maybe, like the displacement at the x position of the ith block. So, we have an x direction here. All right. So what happens is that, what you get is, like this Q instead of in the infinite limit of oscillators, what you get is something that, like, qxi plus 1 minus 2q, sorry, minus 2q of xi. This is a plus qx of I minus 1. And then basically, if you remember the definition of limits, uh, you like the definition of limits, like, okay, df dt is equals the sorry the definition of derivatives. This is limit of, like h goes, sorry, as xi plus 1 go to xi, sorry, of dx. So this is some function of xi plus 1 minus f of xi, as xi plus 1, of this. This is a derivative, and for a second derivative, there's something similar. Is the xi plus 1, or in this case, let's just use delta x goes to 0 of x plus delta x minus 2fx plus f of x minus delta x, divided by 2 delta x. Okay, which is just a extension of the derivative definition, and you can see that this is something that's that looks like the derivative, the second derivative of q respect to x, and this is the derivative of q respect to t, and basically in the infinite limit, so in infinite degrees of freedom, and also the oscillator looks something like, okay, uh something like this equals to c squared over 1 partial to q partial x squared. The c squared over 1 is basically this k over m thing over here. Okay, I think it has the right. Does it have the right? Sorry. No, I think the c squared is here. Okay. Sorry. 1 over c squared is here. This is like the k over m thing at the front. Okay. Um. Yeah. So this is another equation. You can call it the equation for infinite oscillators, or basically this is something we call a wave, right? So if you have like just a rope, which is basic, and every point these are oscillators, and then there are just either in this case it doesn't have longitudinal waves, so you can't think of displacement like this, but you can define the displacement in the y direction. And then basically what you get is a wave. You can have a wave traveling along a rope, all right? Uh, and everything that we have learned before basically also applies to waves. For example, like in 2 degrees of freedom, we have superpositions of 2 different oscillating frequencies, and then we have 2 degrees of freedom there. Okay? In this case, like we have an infinite number of degrees of freedom. So instead of having one omega, omega 1, omega 2 to omega n, instead what we have is omega as a function of something. In this case, it's going to be a function of the, oh, this is a bad idea to write this. Uh, it's going to be a function of some, it's going to be function of some parameter. Uh, let's say, I don't want to use K because K is going to be very confusing. Um, it's going to be a function, a continuous function, because we have infinite number of possible frequencies. And it's really nice uh, because we can have waves of different frequencies, okay? Oscillating frequencies. So each point on this rope, all right, these infinite oscillators are oscillating at, different frequencies, okay, creating this thing. Uh, and because remember that, okay, that different frequencies can't superpose onto each other. So if we have a wave, so a wave that may look like, a cosine of kx, minus omega t. This is the wave. This is something of a wave. Uh, I'll let you show that this is the right thing to write down in the homework. Okay. Plus uh and a wave of a different uh maybe even plus something. Okay. These two wave. Oh, sorry. Please write out. Gotta be somewhere by. Okay, I'm gonna finish now. So linear superposition still applies such that I can add, sorry, this is Q1. Because one of these solve the wave equation and the other thing also solve the wave equation, we can have s- waves that are superposed onto each other. And this is basically the idea of interferences. Okay, so this is a general idea of how, so I couldn't get into much of the detail. So basically I should wrap up. So basically this is the things I missed. And basically I always talk about equation of motion, so I never talk about energies. So that will I will put a section on that on the sheets so you could take a look about energies. I also have okay, I think that's the things I missed the most. I also never talked much into, like solving uh with boundary conditions and also other wave, like most of the wave phenomena. So some of that I will include in the notes. But basically, understanding about multiple degrees of freedom in oscillators and also multiple, and waves is basically uh driven back to, understanding, the first simple harmonic oscillator, and not by understanding it as a harmonic oscillator, but understanding as, displacements from the equilibrium points. Uh and how how the system behaves under such displacements. Okay. With that, I think I should wrap up. All right, so that's all for today. And next week we're gonna talk about central forces and orbital mechanics. Okay. Yeah, so that's it. Any questions? Okay. Yeah. Okay. So if there